7.2 is where we actually learn how to find these areas under the normal curve. So there are actually a number of approaches that you can use to find the area under the normal curve. Back in the day when I was taking these classes and we didn't have any kind of technology, we actually had to use tables to find the area under the normal curve. But now that we have access to technology, that's the approach that we're going to take. And so we're going to be using StatCrunch to find the area under the normal curve. So let's say that we have ball bearings where the mean diameter is supposed to be 1 centimeter and the standard deviation is 0.002 centimeters, because all the ball bearings aren't going to be the exact same diameter. There's going to be variability because of the production process. Let's say that the product that you're manufacturing these ball bearings for require that the diameter be between 0.995 and 1.005 centimeters. Before we get into that, what proportion of ball bearings can be expected to have a diameter under 0.999 centimeters? So here's the gig. X is the diameter of the ball bearing, and we're told the diameter of the ball bearings are approximately normal, and so we draw that curve. We're told that the mean of the ball bearings is 1, and the standard deviation is 0.002. So that would make this value 0.998 at that inflection point, and this one 1.002. 1 standard deviation on either side of the mean.
Right.
We are asking what proportion of the ball bearings is going to be under 0.999. And because we're asking for a proportion, we're asking for the area of that shaded region.
So that includes everything to the left?
Yeah, because we want to know under, meaning less than.
Okay, so all of it then.
Yeah, that whole area.
Okay.
So the question becomes, how the heck do I find that area? To find that area, I have to go to StatCrunch. So to do this in StatCrunch, you go to Stat, Calculators, Normal. You see how, can you see the normal under the normal curve?
Yes.
Yeah.
Okay.
Hardly, but yeah.
Yeah. So that brings up this normal calculator. Okay. With the normal calculator, you have two options up here, standard or between. Standard finds areas under the curve to the left of some value or area under the curve to the right of some value. Between finds area under the normal curve between two values. Okay. So we want the area under the curve to the left of 0.999, where the mean of the normal model is 1 and the standard deviation is 0.002. And so all you do is select, because we're finding the area under the curve to the left, you select the less than or equal to option. If you wanted the area under the curve to the right, you'd pick the greater than or equal to option. So we want the area under the curve to the left of 0.999. Click compute, and you get what do you get? 0.3085. 0.3085. See? That's it. So this area right here, .3085. And so we would say the proportion of ball bearings that have a diameter under 0.999 centimeters is 0.3085. Simple as that. What do you think?
Yep.
Not that bad.
So part B says, what's the probability a randomly selected ball bearing will have a diameter over 1.0055 centimeters? So what do you think we're going to have to do here?
StatCrunch.
StatCrunch.
Well, I mean, you're going to probably create the model again.
Yeah, we'll let
would assume.
StatCrunch build the model this time.
Okay.
Gonna change the sign of greater than or equal to.
Yep. And then this becomes what?
1.0055.
Yeah, 1.0055. We didn't have to change the mean or the standard deviation. And so you can see it's a teeny tiny area in the right tail of the distribution. See it there?
Yep.
So we're getting what? 0.002979. So essentially 0.0030, right?
Mm-hmm.
We write that like this: probability X greater than 1.0055 equals 0.0030. And remember, when we interpret probabilities, we do it from a relative frequency point of view. So if we randomly selected, say, 1,000 ball bearings, we would expect about 3 to have a diameter over 1.0055 centimeters, right? Because 0.003.
If you move the are you saying like you move the decimal points or?
Yeah, it's like that. Oops.
Oh, okay.
0.00. Oh, it went away. 3 is 3 out of 1,000.
Right. You multiply it by 1,000 and you get the 3.
Exactly. Okay. Yep. So that's where that interpretation right here comes from.
Gotcha.
Oh, letter C said, what proportion can be of the ball bearings can be expected to have a diameter between 0.995 and 1.005? That is what proportion will meet specifications. So now, oh, here, let me do this. Let me draw the model just so you can see what we're trying to accomplish here. I'm going to become less specific here. So the area of this region represents the proportion of ball bearings we expect to meet specifications. Does that make sense?
Yeah.
Yeah.
Okay. So we're going to go over here to StatCrunch. And because we want the area between two values, we pick the between tab here in the normal calculator. Our mean is still 1. Our standard deviation is still 0.002. We want the ball bearings between 0.995 and 1.005. Yes?
Right.
Mm-hmm.
Click compute. And there it is, 0.9876. Yes?
Yeah.
0.9876.
76. So we're always doing it to the 1,000th.
Yeah, I'm rounding to 4 decimal places typically.
Okay.
What did I say, 9876?
Yeah.
I believe so.
9876, yep.
Yeah, 9876.
And there you have it. And then from that, you could figure out the proportion that won't meet, right?
Just subtract from 1.
Yep. What would that be? 0.0124, if I can do math in my head.
Yeah, you got it.
Cool, huh?
Mm-hmm. Simple.
Okie dokie. A third interpretation of percentiles. I'm sorry, This third interpretation of area under the normal model is percentiles. You remember percentiles?
Yeah.
So if an observation is at the kth percentile, then k% of all values are less than that value, right?
Right.
And so we want to find in this problem the percentile rank of a home run that traveled 380 feet. So here, to help you visualize what we're going to be doing here, we'll once again draw our model. The mean is 400.3. The standard deviation is 25, so 380 is going to be right around here, let's say. So we want to find this area. That area will be the percentile rank. It's very, very important for you to remember that percentile rank is always area to the left. Always area to the left for percentile rank. Deal?
Yes.
Yep. Percentile rank is always to the left.
Area to the left is percentile rank, correct.
Okay.
So now we do have to change our mean. This is 400.3 and I think this was 25.6. We want the standard piece. Oh, and look at this. I forgot to mention this. This gives you, no, I don't even know. Yeah, this gives you 68.95. So that 1 standard deviation, 2 standard deviation, so on and so forth at the bottom. If you click
that's
that.
really cool.
Yeah. Percentiles are always area to the left. And we want the area to the left of 380. There's the graphic right there on the left. Right? Click compute, and we're getting that the area is 0.2139. Yes?
Yeah.
0.2139. You know, it might be fun now that since I'm brought that up. There's our actual data.
Right.
What I can do here is see this thing called dividers. There's a percent divider that I can put in. And then you can take these bars and move them around. And I can make this value 380 on the nose. And we're getting the actual proportion of home runs that were less than 380 feet was 0.229. You see that? So our normal model, 0.214, is pretty darn close to the actual values.
Right.
And so that's what we mean when we say the curve is an idealized description of reality. Does the red curve describe reality perfectly? No, it's going to be off. I mean, this does a pretty good job of describing the actual outcomes, right? With very few assumptions about what's going on other than the mean and the standard deviation. So that's pretty darn good. So all these people that are trying to forecast what happens with this coronavirus some are using super complicated models and some are using simpler models. So, but all models are going to be wrong.
But some are more accurate than
But some are better than others, yeah.
Gotcha.
And you oftentimes don't know whether your model's good or not until it's after the fact anyhow. So I just wanted to point out that the two are pretty darn close to each other. So 0.21, we're basically saying the percentile rank is the 21st percentile.
Right.
Okay.
And then the other one's telling us that it's the 22nd or
23rd, but
23rd,
that's actual,
yeah,
that's real data as opposed to the model.
Okay.
So according to the normal model, the percentile rank of a home run that travels 380 feet is the 21st percentile. And that's because the area under the curve to the left of 380 is about 0.21.
Right.
Okay. All right. One last idea, and then we'll reverse the process. The normal curve is always extending indefinitely in both directions. And the phrase that we use is it's asymptotical to the horizontal axis. And so just be mindful of the fact that if you ask to find the area under the normal curve, say to the left of 40, where the mean is 15 and the standard deviation is 2, mean is 15, standard deviation is 2, what's the area under the normal curve to the left of 40? See how StatCrunch says 1? It's not quite right. It's really like 0.999999999 with a bunch of 9. And so StatCrunch just says it's 1, but it really isn't. You just need to be mindful of that.
Okay.
The odds of that happening are pretty slim, because if you saw an observation of 40 with these parameters, mean 15, standard deviation 2, you'd wonder what the heck is going on, right? And likewise, if you said, what's the area under the curve to the right of 40, it's going to say 0 when it really isn't. It's more like 0.0000, tons of zeros, and then maybe a 1.
Oh,
right?
okay.
Because the curve approaches but never touches the horizontal axis.
Right.
So, I mean, the chances of that happening are pretty slim. And so all we said is, what we would say is, if you were asked to find the area under the curve to the right, I'm sorry, to the left of 40, just say it's greater than 0.99999. Okay. And then similarly, if the software reports an area of 0, we'll say it's really small, less than 0.0001.
Right.
You're going to see that more often when we get into chapter 10, computing something called p-values. So stay tuned for that.